Okay, sorry I'm not here today to go over this in person. I know it's probably pretty lame to have to watch yet another video when you weren't going to have to, but I'm going to try to keep this to like 5 to 6 minutes. So I'm going to be probably talking lightning fast. Of course, I say that, and I am known to ramble. So we'll see what we can do. We'll cover any questions you have about law of definite and multiple proportions and doing those calculations hopefully tomorrow when I'm back. So a lot of the stuff that we're talking about here today is review from last year. So Dalton's atomic theory. Remember, the first modern atomic theory that came along was John Dalton's. This is in the early part of the 1800s. He had four main postulates. I think we broke this up a little more last year, but the postulates were: one, all matter is made up of atoms; two, atoms of a specific element are identical, and atoms of different elements are different; three, chemical compounds are formed by combinations of elements; and four, atoms organize in chemical reactions to form different compounds. Dalton's atomic theory explains mass laws. So conservation of mass, atoms cannot be created or destroyed. They cannot be converted into other types of atoms. So atoms are atoms. You can't turn hydrogen atoms into oxygen atoms. Since every atom has a fixed mass, during a chemical reaction, atoms are combined differently, and therefore there is no mass change overall. So like we talked about last year, matter present before the reaction has to be present afterwards. The mass before and after is the same. Also, Dalton's atomic theory explains law of definite composition. Atoms are combined in compounds in specific ratios, and each atom has a specific mass. Okay, so water is always H2O, specific ratio, and each atom has a specific mass, so each molecule of something like water has the same mass. Each element has a fixed fraction of total mass in a compound, so we're talking about mass fractions. So the amount of mass hydrogen contributes to the overall mass of water, and oxygen to water as well. Also explains multiple proportions. Atoms of an element have the same mass, and atoms are indivisible. When different numbers of atoms of elements combine, they must do so in ratios of small whole numbers. So here's carbon monoxide and carbon dioxide. Again, whole number ratios: one oxygen to carbon, two oxygens to one carbon. This would have a multiple proportions ratio of 2 to 1 due to the doubling of oxygen for each carbon. Then we get moving forward, discovering the electron. Remember, J.J. Thomson is responsible for the discovery and defining the electron. He worked with cathode ray tubes. Here's an example of that. Some of the observations that he made: one, rays bend in magnetic fields, which means this consists of charged particles. Electrically charged particles, when they're in motion, they emit a magnetic field. So if you shoot electrons through this magnet, the magnetic field is going to cause the electron beam to bend. Rays bend toward positive Plating electric field. That happens. That means that the electrons had to be negative because opposite electrical charges attract. And ray is identical for any cathode, which means whatever this particle was, it was found in all types of matter. So all types of matter, all atoms contained the electron. Discovering the electron's charge with Millikan's oil drop experiment. This is a pretty famous experiment. In order to do this, we have this large canister type device with an atomizer. The atomizer is right here. If you've never seen one of these, maybe in old movies where a lady has a perfume bottle that looks like this and she squeezes it and it sprays a fine mist. So in step one, a fine mist of oil is sprayed into the apparatus. Two, oil droplets fall through a hole in a positively charged plate. So you have all these little tiny droplets of oil, and it goes through this opening. Three, X-rays knock electrons from surrounding air, which stick to the droplets. Finally, four, I guess not finally, but four, electrically charged plates influence the drop's motion. So with these oil droplets gaining electrons, they're going to have negative charges. And with an electrically charged plate, and that plate being positively charged, there's going to be an interaction. It's going to change the motion of that particle as it's falling. Okay, positively charged plate, negatively charged particle, they're going to interact. And then five, observer times drops motion and controls the electrostatic field. So in doing this, they could slow the descent of the drop with the electrical charge, and based upon the amount of electricity required in order to make that work, they could figure out what the charge was of the electrons. Okay, and that's why I had to observe it and make sure the droplets were sitting in place. And then we have Ernst Rutherford and his gold foil experiment. So we have the device. Step 1, radioactive sample emits a beam of particles. Remember, these are big particles called alpha particles. They're roughly the size of a helium atom's nucleus. So a helium atom's nucleus has 2 protons, 2 neutrons. So it had 4 big particles in it. Beam of alpha particles strikes the gold foil. In step 3, flashes of light produced when alpha particles strike zinc sulfide screen show that most alpha particles pass through foil with little to no deflection. Minor deflections of alpha particles are seen occasionally in part 4. Part 5, major deflections of alpha particles are seen very rarely. And then in order to explain those behaviors, we have these alpha particles going straight through with little to no deflection. That occurs because within the atom there is very little matter within the atom. Most of it is in the nucleus. So on the right hand side here we see some particles that travel straight through. The big goldish part of that would be the space that the atom occupies, but most of that is empty space. Okay. On occasion we do get some of these particles deflecting. So if they come in and they hit a nucleus is an incredibly dense pocket of matter, so that alpha particle would slam into that gold nucleus, which in comparison to the alpha particle, the gold nucleus is enormous. Hits that, boom, comes back, and occasionally some of these come through and are deflected a little bit. The alpha particle has a positive charge to it. The nucleus, of course, is an overall positive charge, so if the alpha particle passes very close to that gold nucleus, it's going to push it away a little bit, and that's where we get those minor deflections. So this is where Rutherford and his team figure out that atoms are mostly empty space, but there's a very dense core that seems to have a positive charge. So now we get into a more recognizable model of the atom from other things that we've talked about in the past. So again, this red kind of cloud here represents where the size of the atom, electrons would be somewhere within that red cloud, but then we have this really dense nucleus where there's protons and neutrons. Here's the names of our subatomic particles, their relative charges, +1, 0, and -1. We have their absolute charge in coulombs. That's what that big C is. It's not degrees Celsius, it's big C for coulombs. Their relative mass, their absolute mass given in grams, and then their locations within the atom. Atomic symbols for isotopes. We did some of this last year, and we can talk about more of that on Wednesday. Same thing here. I don't want to get into this in the video. We can talk about this in class on Wednesday, the calculating of atomic mass from an element. And then the modern reassessment of atomic theory. Number 1, all matter is composed of atoms. The atom is the smallest body that retains the unique identity of the element. 2, atoms of one element cannot be converted into atoms of another element in a chemical reaction. Elements can only be converted into other elements in nuclear reactions. Nuclear reactions are different than chemical reactions, and we're not going to get into nuclear chemistry. I should back up too for number 1 here. The atom is the smallest body that retains the unique identity of the element. If you were to break an atom down into protons, neutrons, and electrons into its individual components, those are like the building blocks of atoms. So you would not have any element at that point. You would just have random subatomic particles. 3, all atoms of an element have the same number of protons and electrons, which determines the chemical behavior of the element. Isotopes of an element differ in the number of neutrons. We talked about that last year, which also changes their mass number, and again, we'll get into that stuff more tomorrow. Compounds are formed by the chemical combination of 2 or more elements in specific ratios. and that was what we talked about, the law of definite and multiple proportions. So that's it. I know that was really quick. Maybe you have questions. Ooh, and I went 10 minutes, which is not what I intended to do. Okay, so I'm going to stop there. Go ahead, work on homework the rest of the time. Do as many questions as you can. Otherwise, save all your questions for tomorrow. Or you can email me, post them to Edmodo. Remember, if you have questions, post them to Edmodo as soon as you get them, because I can respond to them right away. And then you don't have to wait till class the next day. Okay, thanks.